All right. Welcome to this talk about glassboxing, modeling decisions in simulations, and the main question, why do chords get smaller or have gotten smaller in specifically the Baltic Sea? First up, quick question round. How many of you know the term black box? Okay, glass box. Modeling in a computer science or as a scientific method? Okay. For black box, most of you raised your hand. From which context do you know the term? Is it from, for example, software testing? Is it from AI and like explainable AI and stuff? Okay. Is it from didactics and the like type of scaffolding it represents? Okay, a few. Well, let's leave the unimportant stuff behind for a bit and focus on the main thing. Why do chords keep getting smaller? Do any of you know why that is the case or why this has happened? Oh, great. Then we're all going to learn something today. To start off, I'm going to show you a simulation. This simulation was created as part of a seminar at the Freie Universität Berlin, specifically an agile software engineering seminar with Yamur Dönmes, Murat Efe, Konstantin Oltmann, myself, and with the help of the Department of Didactics of Biology at the Freie Universität Berlin, with Christina Fricke, who acted as our customer, who asked us to create the simulation. As you can see, here we have a bunch of chords swimming in the ocean, a little bit abstract. We didn't have the budget for 3D animated fish. And now we can just start fishing. And maybe just by watching a few iterations of the simulation, you might begin to get an understanding why chords are getting smaller. All right, how many of you would now say you have at least an idea of what has happened in the past and what might continue to happen? All right. What you've just witnessed was what I would call a black box simulation. You only interacted with the simulation, or I, in your stead, have interacted with the simulation through the intended user interface. I did not give you any additional information or things about our implementation and models inside the simulation. You just saw what happened. Now, as we continue this talk, I'll try to give you a little bit more insight into what we did during our development and what are the models behind it. Okay. A little bit about modeling in this context. What do I mean when I say modeling, and specifically what do I mean when I say we programmed this? When we create a program, when we do software engineering, we take, for example, a phenomena in the real world or something that we imagine, something that does not yet exist in the real world, and with a certain purpose, we remove ambiguity, we highlight certain things, we create abstractions to create, in the end, a model. And this model is then encoded. We code in a certain programming language, for example, and create our computer program. So a simulation, in the end, is nothing but an executable model of, in this case, caught in the Baltic Sea. Now, I want to show you a few of our iterations. It was an agile software development project. We had 4 weeks in total, so we did 1 iteration per week and created 1 prototype every week to see where we come from, some of the decisions that we made, and maybe some of the things that could have been done a little bit better, let's say. This was our first iteration. As you can see, some of the things are similar, some of them are not really there yet. Our goal in the beginning was to get a sense of the user interface, and so we and our client have something to talk about. You can see the diagrams are already there with different colors, but you can also see that, for example, these colored dots on the fishes, they look a little bit wonky and a little bit different. What are they? These are, this is the second one. These are what's called alleles. It's from biology. Multiple alleles, or two in this case, make up one gene, and these genes influence the size of the fishes. In this case, we have 3 genes that influence the fish size. One are the triangles, one are the squares, one are the circles. In reality, there are more genes that influence fish size. In this case, we reduced the complexity, we did abstraction. However, in the first iteration, we misunderstood our client. We just didn't really get what she was saying, so we made one color for each symbol, so to say. What are some other decisions, modeling decisions, that we took in the beginning? We decided to store our alleles in a 2-dimensional list, with the first index being the fish and the second index being the index of the allele. We also decided to use prototyping. We created one fish and one allele, and when we need them, we create a pool of them and change their attributes. These types of modeling decisions we did together on our meetings, because in the beginning we had a problem. We said, hey, we want to do the UI, we want to do that the fish exist in the first week, but we didn't really talk about how we wanted to do this. So each one of us did our assigned tasks, but we did not really talk about how we are going to do this. So in the end, our pieces didn't fit together. This ended in us sitting for initial 1 or 2 hours and redoing some of the things that we had done previously. So in our further meetings, we decided, okay, when we have major decisions to do, we have major modeling decisions, we're going to take these decisions together. And then, in the end, what's left after we've created our model together? Well, we have to encode it. And that's what we did in the end in our work by ourselves. What? Okay. Okay. Stuff is back. Okay. Well, anyway, let's continue. You, as good as. Okay. Where were we? So during our development process, we had these multiple iterations, and the modeling decisions we took together. Thank you. Now, this is what was the result of our seminar. This is the code we came up with, and you can already see most of our logic is in this great, beautiful wall of blocks, let's call it. And I dare say that if I were to give you this project, the project file with the code, you wouldn't really call this a glass box. If you were a tester, one could say, yes, this would be glass box testing, because I've given you my entire source code, and any tests you design have access to all of the underlying code. But even if I were to try to make changes to the code at this stage, I'd have to get back into it for 10 to 15 minutes, I'd say. So we can't really talk of a glass box at this point. So why can't we talk of a glass box? Well, when I say I want a glass box simulations, what I'm talking about is that there is additional info given to the user about the underlying models, but in a comprehensible form. In the end, this is information about the underlying model. It is the underlying model, but it's not given in a form that can be easily understood. So, what is it that we should do, that we would have to do, to use one of the great aspects of Snap, that we have a low floor, that we do not are hindered by, for example, C syntax or something when we try to share our projects? Well, what we can do, or what we can try to do, is reduce the complexity and turn the project into something that is more easily understood. Because with Snap, we also have the advantage that if we want to share our projects with everyone, we can just do so, we can just publish. And others can look at our projects and say, hey, that's cool, I want to do something with this. But the problem is, if I see the code simulation and think, hey, that's cool, I want to further do something else, and then I look inside and I see this, I'll probably not be very encouraged to do so. So, what should we do? Well, we should at least try to glass box the things we do. Try to make the models, the underlying decisions, the architecture as comprehensible as possible. This is not something we can universally achieve. It's a race for perfection, so to say, but we can try our best. And I personally would say, even this, I'm going to be honest, I'm not 100% satisfied with the state this is in, and there are always corners you can continue to try to improve. But yeah, we can try to do so. Now, let's get back to the code and maybe an explanation. Some of you already raised your hand that you've gotten more of an idea. But what is it that's happening? Or what is it that we're doing in this simulation? Well, in the real world, fishermen, they want the biggest fish. They want to get the biggest fish when they fish, and the small one, they either go through the nets or they throw out. So what is it that we're doing in our simulation when we go fishing? Well, we fish out the biggest fish. And when we reproduce, the remaining fish, the allele, they get duplicated and they populate a new generation. Is this how it's 100% happening? No, we have some limitations due to our modeling. For example, we have to cut the generation in half because we repopulate by duplicating. So we can't really say, okay, we're only going to fish out one of the fish. But in the end, this reduction, this abstraction of reality can be used to convey a certain idea. And that is the pressure that is exerted by humans on nature due to unnatural selection, so to say. Okay. Maybe if you want to use the simulation, I've also published it, so you can click through it yourself. In the end, what was my whole point? When you create your simulations, when you create any project for that matter, try to be as transparent as possible, try to glass box the things you do as much as possible so that others may be encouraged to remix your projects, to further their work, and so that we can have more collaboration and are not failed, let's say, by spaghetti code and unreadable walls of blocks. Yeah. Thank you very much.